I'd like to now ask to the stage Professor Uri Banin, the founding member of our Nano Center. Uri is going to tell us the exciting technologies that he was able to invent. Uri, please.
Thank you very much, and good afternoon. So I will tell you about scaling breakthroughs in nanotechnology. Actually, why are we going nano? Well, you know, you've heard already, this will be the fourth talk of members of our Nano Center, and by now you should have been persuaded that actually nanotechnology addresses each and every one of humanity's challenges, being energy, which I will talk about in the second part of this presentation, environment, communications, healthcare, and also in the area of homeland security. And acknowledging this early on in the early 2000s, we have founded the Center for Nanoscience and Nanotechnology. This center encompasses 85 research groups from all disciplines of the university. So this is what is so beautiful about nanoscience. It's so interdisciplinary. We have members from chemistry, from physics, from engineering, from life sciences, medicine, pharmacy, agriculture, and we are all interested in what is tiny. And so what is tiny is demonstrated here. These are quantum dots, nanoparticles, semiconductor nanocrystals, which are only a few nanometers in diameter. They contain a few thousand atoms, which are arranged just like the structure of the bulk semiconductor from which they are derived. And why do we struggle to make them so exquisite and so small with precision is because of size-dependent effects. And basically, the first effect that I would like to talk about is color. So what you see are red solutions, which are particles of this type that are only 6 nanometers in size. They have 3,000 atoms and emit red light. But when we make the particles smaller and smaller, we can tune the emission color such that when we go to 2 nanometer particles with 200 atoms per particle, they emit blue light. And in between, we get the rainbow of colors. So here we have already a functionality derived by the unique size effect in the nanoscale. And we can put this functionality into action into displays. This is the first function that we would like to use in displays. Another functionality we can gain from furthering the control that we have over the material. As you see, we can grow these nanorods, which are elongated. And why do we do that? Well, nanorods offer the color control that I've described by changing their diameter, but they offer additional properties. For example, they will display polarization. This is another characteristic of light, which is actually known to you perhaps from polarizing sunglasses or from going to 3D movies which use polarization to generate a 3D image. And importantly, this joins up with color for another feature which is central for liquid crystal displays, which are based on switching polarization on and off as a method of making an image. So taking all this together, what we need furthermore to actually apply this is the use of chemistry. And we use chemistry to generate a cost-effective and scalable approach to synthesize such particles on a large scale, which makes them applicable. And beyond that, we also have the opportunity to manipulate these materials, because what we have is actually a semiconductor in a bottle, in a solution. And that means that we can be very flexible. We can put this in water for biological and medical applications. We can print this together with Shlomo to get pixels. We can put it in a plastic film, which can later go into your screens, as I will describe shortly. And this flexibility, combined with color control, combined with polarization, makes this very functional. And this has led me to found, back in 2009, a company which we spun off together with Sisum to actually commercialize the use of these kind of nanocrystals in displays. And this is just an example of how we encourage at the Nano Center the operation and the movement from science to technology, into companies. So this was enabled by having Qlight, the company that I founded, use extensively the facilities and the infrastructure of the Nanoscience Center. Now what we did was to team up with a strategic partner, which is Merck. Merck is actually the company that makes most of the liquid crystal molecules that actually power up liquid crystal displays. So they have an obvious interest in display technologies. And this kind of strategic alliance has led to the use of their ability to actually help in upscaling the synthesis of such materials, as well as open doors into the display makers, which are the customers of this type of materials and this type of technology. So Qlight was fully acquired in 2015 by Merck, but it keeps operating within its facilities in Jerusalem as a global R&D center for quantum materials for Merck. So this is the story of Qlight. And what Qlight does is really develop nanorod and nanocrystal-based technologies for liquid crystal displays. And just to give you the reason for that, well, we're all surrounded, especially in this room, with so many displays. You have displays in your pockets, in your car, in your home. And what is still needed in this very ripe technology is that we still strive for actually better colors, because we all want to see the right image on the screen as lifelike as much as possible, as well as long battery runtime, which is especially critical for the mobile displays. So the first thing that shuts off in your mobile phone when you don't use it is the screen, because this is the #1 eater of energy in your mobile phone. So we have here materials that are functional. They have the color, they have polarization, and we can put them flexibly into different materials. And what we have done is introduce an active brightness enhancement film, which is a way to enhance color in the light, the backlight unit of a liquid crystal display, such that the color that you will see in the display will be much more enhanced. What we use is actually blue light emitting diodes in the backlight, which actually give the blue light for the blue pixel, as well as green and red nanorods, which are well tuned to what we need in order to generate a lifelike image on the screen. And we also utilize the polarization effect in order to further enhance energy saving opportunities. And this is the idea of the ABEF, to actually achieve well-controlled colors and highly saturated images, which when you see such a screen, you see that you really want this screen to be part of the way that you actually image and look at the world. So this is an example of how we partner together with a strategic partner and put our nanoparticles into action in displays. And what next? Well, we've heard this morning Professor Korenberg, the Nobel laureate, identify the challenge of the 21st century in energy, which I very well identify with. And nanotechnology has a lot to do with addressing this challenge. Particularly interesting is solar energy. Just imagine that in 1 hour, the amount of solar energy that hits the planet Earth is sufficient to supply the entire population needs for 1 year. So if we can only harvest a part of this energy, we have a sustainable and clean form of energy that we would like to use. And deploying solar energy towards conversion of solar energy to electricity is actually out there in the market, photovoltaics or solar thermal. But what will you do when you have to drive your car or go on the bus? In this case, we need a solar fuel. And what we need to do is imitate, in a way, what plants are doing to harvest energy from the sun, to actually take CO2 and generate sugar, to generate energy, to generate glucose. And so we need to actually solve this problem and address this for transportation. And so one approach to do that, a solar fuel like that can drive your car, is actually hydrogen. Hydrogen is abundant, it's in water. A glass of water, H2O, has a lot of hydrogen. And the problem is how to get it out of the water, how to generate the solar fuel. We would like to do that with sunlight in order to generate from the solar energy, the chemical energy, and the fuel. And to do that, one way to do it in a clean manner is to use a photocatalyst, a material that will absorb the light and actually have this ability to break water and get hydrogen out in a clean, sustainable manner. And to this end, once you have this hydrogen, you can already use it today in existing cars and existing buses, which are actually run by fuel cells, which are fueled by hydrogen. And what fuel cells do are take hydrogen and oxygen and generate electricity, which can feed the motor, the electrical motor of these clean cars. And the product is water. You get back water. So it's a very clean cycle of generating alternative energy. Now, the problem is to get at this photocatalyst. So this is something that really combines materials, nanoscience, chemistry, and physics. We try to get there. This is a great challenge. And we're talking about hybrid solutions. And these are hybrid nanoparticles combining semiconductor and metal particles together, which we invented over a decade ago. And it turns out that these particles actually have a synergistic effect. You get combination of properties from both materials which are better, which are more than the sum of their own properties. And these materials are actually photocatalysts. They can act in this functionality of actually putting them in water and having the light absorbed by the semiconductor, electrons can then actually go to the metal, and this small metal tip is actually the catalyst that can break water and generate hydrogen in a recyclable and clean manner. Now, what you will do is use this in this bus, which has a very nice concept, because you see that on the door, they've decorated and put H2O, which is the molecule of H2O. When you open the door of the bus, it means that you broke the hydrogen and you use it in the motor to drive it clean, in a clean fashion. And then what you get as an emission is just water. You get back only water. So this is really a clean cycle, which we hope to contribute to. Now, energy is a very important challenge, and it has its hurdles, and it will take time to get to this technology. In the meantime, we've identified other applications using the photocatalytic properties of these hybrid nanoparticles. And it really resonates and relates to what Professor Magdassi, my colleague, which we collaborate with on this project, has talked about. 3D printing. We heard about the wonderful things you can do with 3D printing, but it turns out that there is a gap in materials for 3D printing, and this is how to do it in water. Usually it's done with light, but the materials that are used are typically plastics that are common in organic solvents, but not in water. So there's a gap there. And in fact, water-based printing is important because this is a lot of the biomedical applications will depend on that. If it's, for example, drug delivery elements, contact lenses using hydrogels, or at the ultimate end of this, printing organs. So we want to have the ability to print in water. And indeed, our nanoparticles, these hybrid nanoparticles, can be photocatalytic and help and serve as photo-initiators in this printing application in water, and be used in this 3D printer to actually initiate the polymerization process of the plastic that we can write exactly where we want it in water. And indeed, we were able to demonstrate this very recently together with Shlomo to actually print this intricate structure, which you see that can use our hybrid nanoparticles as photo-initiators in this process. And on top of that, we can actually add nanoparticles that will make this also luminesce, will give you also another functionality of light emission. So we do hope that this can be used in the future to open up opportunities for 3D printing also in water environment for various biomedical applications. So I've told you about how we put nanocrystals into screens. I've described to you the vision, the farther vision of using hybrid nanoparticles for energy applications, for making solar fuels. And in the meantime, in the intermediate timescale, how we can view the use of these particles in 3D printing and other applications for water-based manufacturing. And we have also interest in using these kind of nanocrystals in biological applications, as well as in printed electronics applications, where we can use the functionality of this liquid phase semiconductor in a new way to make, for example, flexible devices. And this is basically the time to call for what we are looking for is discussion, is partnership, to really identify what kind of new applications, where the capabilities of our unique technologies with nanocrystals can be applied. And I open and welcome you to actually discuss with me such ideas that you may have of needs where our nanoparticles can help. Beyond these very important products, I would like to acknowledge and thank my research group and say that definitely the most important product that we generate at the Hebrew University at the Nano Center are these very amazing young students that are really the future of both the Hebrew University, of academy in Israel, as well as the high-tech industry. Thank you very much.